Good afternoon, everyone. Thanks for coming to the talk. First of all, let me ask you a question. How many of you use Electron applications? Can you please raise hands? Quite a lot. How many of you use, to be more specific, Discord desktop application? Microsoft Teams, Slack, Twitch, VS Code. So most of the people here use Electron applications, right? What if I told you that I could have hacked or owned all of your computers just by sending a link or a message? Isn't it scary? So hereby, I welcome everyone to ElectroVolt, where I'll be sharing the details of how we are able to hack all these desktop applications while uncovering the new attack surface on Electron. My name is Mohan Krishna Pedapati, also known as Sirius. I'm currently working as Application Security Auditor at Q53, and I like browsers, CTFs, and blockchain these days. I'm also captain of the CTF team Invaders. So the agenda for this today's talk is, first, I'll be talking about the basics of Electron, its architecture, and its security preferences such as web preferences. Then I'll show the case studies of the applications we hacked by starting with exploiting the known Electron vulnerabilities and moving on to the new attack surface we found on Electron applications. And finally, we'll go over the mitigations. And without any further ado, let's get started. So what is Electron? It's a negatively charged subatomic particle. It's not that. I'm just kidding. It's a popular cross-platform desktop application framework. If you can build a website, you can build a completely native cross-platform desktop application using Electron. This is the main motto behind Electron. So with just HTML, CSS, and JavaScript, you can build a desktop application very easily. So as it is very easy to build desktop applications, it is used by a lot of companies like Microsoft. So they use in VS Code, Teams, Discord, Slack, and 500 plus more applications. So before diving into the bugs, we need to first understand the architecture of the Electron. So as you can see on the slide, there are mainly two types of processes. The main process and the other one is the renderer process. The main process is the starting point of the Electron application. It manages the Windows or renderer process using browser window API, and it also has access to native graphical user interface APIs such as menu, tray, and so on. And by default, the Electron main process runs in JavaScript context with Node.js enabled. On the other hand, we have the renderer process. The renderer process, as the name implies, are responsible for rendering the web page content, which means it follows the Chrome web standards, and it is same as Chrome renderer process. And these main process and the renderer process are analogous to Chrome browser process and the main process, browser process and the renderer process, except the main process here has JavaScript context enabled. So the node shared library, which is on the right block, is accessible to both renderer process and the main process. But as it is not safe to directly expose the node shared library to the renderer process, because if you allow node access to the renderer process, with just accesses, open the redirect, you can get remote code execution. So it is not safe, right? So there are certain web preferences which are used which are in the Electron renderer process to restrict the access of the node shared library. We'll be talking about more about this in the coming slides. On the right block, we have the IPC module. The IPC module is responsible for the communication between the main process and the renderer process. So let's see a basic Electron application to better understand how an Electron application looks. On the left block, we have the main process. The main process, starting a new renderer window using browser window API, with some web preferences. And within that window, it's loading google.com URL in it. And as I said, there is a communication between the main process and renderer process, right? So you need to start an IPC event listener. So here, it started an IPC main.on open URL event listener, which is expecting an URL and sending it to shell.open external sync, which is a dangerous sync. We'll be seeing more about this in the coming slides. So this is basic main process. It creates a renderer process with some web preferences. So let's first understand the web preferences. There are mainly 4 web preferences we need to understand. The first one is sandbox, then node integration, preload, and context isolation. So let's first understand the sandbox. The sandbox web preference, as the name implies, sandboxes the renderer process. It is similar, it is same as Chrome sandbox, where in Linux, it is seccomp, and in Windows, it is Win32k lockdown. Okay, so if the renderer process is sandboxed, we can't run a memory corruption bug and get remote code execution, because the bad syscalls will be blocked by the seccomp in Linux and Win32k lockdown in Windows. So it's always good to enable this web preference. And next we have the node integration. So it tells if the renderer process should have access to the node shared library or not. And as I said, as it is not safe to directly expose this node integration to the renderer process, Electron developers introduced something called context isolation, where the JavaScript context with node primitives is completely different from the actual web page JS context. You can see in the slides that the application web page JavaScript context is completely different from the node primitives and IPC modules JS context. So if you get an XSS in that application JavaScript context, it is there is no use. Like, you can just steal cookies but can't access node share library. So that's why you should always use context isolation. So this is the same concept used in Chrome extensions, where Chrome extensions content scripts are isolated from the actual web page, and they call it an isolated world. Within this isolated world, only the extensions JavaScript will be run. And we can't access the JavaScript context from the web page JavaScript context. So within that isolated context in the Electron, the preload scripts will be run. And so if the context isolation is enabled in the renderer process, it is not possible to access the node share library from the application web page JavaScript context. So let's finish our Electron application. So on the top right block, we have the preload.js. As I said, the preload.js runs in an isolated context, and that isolated context has access to more sensitive APIs such as Electron, IPC module, and node internals. So we need some way to expose some APIs to the web page, right? So we use context bridge API to expose electron.open URL to the web page. And in the top and in the bottom right block, we have the web page, which is loaded within the main process. So there it is accessing window.electron.open URL and sending the path of the current user's calculator. So it sends to the preload.js. From there, the preload.js uses IPC module to send the message to the main process. So there it will execute that URL in shell.openExternal, which means it will pop a calculator, because it is a dangerous sync in Electron, where if you provide the part of the current directory binary path, it will execute that. So the least restrictive the web preferences are, the more vulnerable your desktop application will be. So you should always enable sandbox, disable node integration, and enable context isolation. As you can see on the slide, the browser window is created with sandbox disabled, node integration is enabled, and context isolation disabled. This is the least restrictive Electron application. So XSS in this Electron application will be equal to RCE. So it is never good to use these web preferences. So throughout this talk, this is our attack surface. We are attacking the renderer processes of the Electron application where our JavaScript will be run. So we'll use XSS, open redirects, deep link misconfigurations and all to exploit this renderer process. And finally, our goal is to get remote code execution. So we are going to start by abusing the least restrictive Electron configurations and then move on to complicated exploits. So to make slides neater, let's use these terminologies. Okay, let's see our first case study. So assume an Electron application where it's using the node web preferences, node integration is true, context isolation is false, and sandbox is false, which means it is the least restrictive web preference, which means XSS is equal to RCE, and it is a bad Electron application because it is very easy to get shell as node is exposed in the renderer and it is not sandboxed. So we just need to find a way to embed our JavaScript. We don't even need an XSS there. We just need to find a way to embed our JavaScript and get remote code execution. So this is where we are in the architecture. The red circle is showing the renderer process where it is not sandboxed, and IPC modules and node shared library is directly available. So let's see the first case study using these web preferences, which is VS Code RCE bypassing restricted mode. With this bug, we were able to achieve remote code execution in VS Code when a victim opens a markdown file in an maliciously crafted VS Code project or a folder, even in restricted mode. So the summary of this bug is VS Code allows rendering of markdown files, you know, right? In an iframe with protocol VS Code -WebView. So, but with a strict CSP, which means you can't get the XSS, and most restrictive web preferences. So there is sandbox enabled and node integration is disabled. But the main window of the VS Code, which has node integration enabled, uses an interesting protocol handler named VS Code -file, which works similar to the Chrome file protocol, but the catch here is the VS Code -file handler protocol allows the navigation from the cross origin. So the idea is to, if we can find a way to embed our JavaScript, we just need to create an HTML file in the victim's computer and navigate to that HTML file using VS Code -file protocol. And there we can have access to node integration and pop the calculator. So this is the complex attack chain we use to get remote code execution in VS Code. So I'll try to explain, but you can find my blog and there you can see the full exploit and write up about it. So let's see. So when a victim opens pawn.md file, so it redirects the victim to attacker site where our JavaScript will be run in step 2. Then I forgot to tell you that the green color window is the most restrictive web preferences window. Their sandboxing is enabled and node integration is disabled. Here it is very hard to get remote code execution. But the window which is in red has node integration is enabled and sandbox is disabled. There we just need to find an XSS and use node modules and get remote code execution. So we are in step 2. In step 2, we found an interesting post message misconfiguration where if you send a post message to green color window, it gives access in that window. So it's a nice feature we have in VS Code. So using that post message, in third step, we were able to get access on yellow color window. From there, we exploited one more post message issue on VS Code red color window to read the current user's directory location. So now we have the leak of the current user directory location, right? From using that user directory location, we can just navigate the yellow window to red color window using VS Code -file protocol handler, and there we can execute the node modules. So let's see the demo of this bug. So, sorry. So victim opened a VS Code markdown file. It rendered and popped the calculator. So that's a nice bug which uses a least restrictive web preferences, right? So let's increase the restrictiveness a little bit more. Now assume that the context isolation is enabled. which means we can't directly access the node modules. So in the previous bug, we used node module require child process and call get access to system calls, right? Now we can't do that because context isolation is enabled. As the context isolation is enabled, we can't access node module. So there are two ways to exploit this bug. We can either use a renderer exploit, which means we use a V8 exploit to get remote code execution because the sandbox is disabled, and or we need to somehow find a bug which is not available, which is disabling context isolation somehow. So let's see how we can exploit this. And this is where we are in the architecture. As you can see, the application JavaScript context is different from the node primitives, IPC primitives, isolated context, which means we have, even if we have accesses in application JavaScript context, we can't access node modules. But the catch here is it runs in non-sandbox renderer, which means we can use a memory corruption bug to run a V8 exploit and get remote code execution. So let's see the case study 2, which uses the Discord. The Discord is using the same web preferences where node integration is disabled, context isolation is enabled, but the sandbox is disabled on the main window, which means we just need to find a way to embed our JavaScript and run the V8 exploit there and pop the calculator. So at the time, it was using Electron 12.4.1, which means it's indirectly using an old version of Chrome. And Chrome usually has a lot of V8 exploits, JIT exploits. V8. So we found an XSS in one of the iframe embeds, but the thing in Electron applications is the iframes are usually sandboxed, which means we can't run the V8 exploit and pop the calculator. But we found an Electron new window misconfiguration. Using that new window misconfiguration, we opened a new window. So we are escaping that from that new window and navigating that window to exploit. So there we don't have sandbox enabled. So there we can just run V8 exploit and pop the calculator. Let's see the case study, demo of this bug. So as you can see on the slide video, I'm pasting a link and it's rendering a video. And whenever a victim clicks on that link, it creates a new window. And in that window, the V8 exploit runs and pops the calculator. So that's the Discord RC. That's fun. And Discord paid us $5,000 bounty, even for that nice exploit. If you sell that exploit, you'll get a lot more than that. Discord fixed it by fixing the new window misconfiguration, and they upgraded the Electron version. So that's fun, right? Let's increase the restrictiveness a little bit more. Now the sandbox is enabled, which means even with the JavaScript execution, we can't run a V8 exploit and pop the calculator because it is sandboxed by seccomp in Linux and Win32k lockdown in Windows. So we can't access bad syscalls like open, write, execv. So we can't pop any calculator with that. So, and also the node modules are not exposed in the renderer. But as you can see, the context isolation is disabled here. So can we use that context isolation disabled window and leak Electron internal modules such as IPC? And using that IPC, even though our renderer process is sandboxed, can we make the main process to do bad stuff for us? Let's see. So this is where we are in the architecture. The whole application JavaScript context, preload JavaScript, and Electron internal code all run in a single JavaScript, V8 JavaScript context, which means we can mess up Electron internal code and leak IPC modules and other modules from the renderer process. So let's see the ways to get shell in this renderer process. From Electron version less than 10, there is this module called remote module, where from the renderer process, if you send a JavaScript to the main process, it will execute that main process. It will execute the JavaScript there. It means you can just send a Node.js and it will execute there. I don't know why they developed this remote module, but So it's like a sandbox bypass, right? We are sending a JavaScript to the main process, and the main process is executing your Node.js in a non-sandbox renderer process where Node is available. So they obviously thought it's not really good to have this remote module, and they put it behind an flag, which means the Electron developer has to explicitly enable it. So if the application explicitly enables it, you can use this remote module to pop the calculator, or you can use an IPC misconfiguration, which is similar to the remote module. And I'll be talking more about this in the coming slides by showing an exploit in Microsoft Teams. So now, the latest Electron versions is completely removed the remote module, which means we can't use the remote module at all because it is not safe at all. So they removed it completely. So here, the ways to get the remote code execution is find the Electron specific IPC misconfigurations or application specific IPC misconfiguration. So we need to, even with the context isolation disabled, we need to somehow mess up with the Electron internal code and leak the IPC module. So this is the gadget we used to leak the IPC module. This kind of attack was first introduced by my colleague Masato Kinugawa. So he was the one who found the context isolation. He was the one who is responsible for Electron developing context isolation. And so using this prototype pollution gadget, we can mess up with Electron internal code and leak the IPC. So with that leaked IPC, what we can do is, so here you can see we are leaking the webpack required, and we can get access to all the Electron internal modules. You can find more about this in my blog. This is a little complicated to understand on the slides, but if you can debug and see in the Electron, you can understand the prototype pollution gadget. It's just messing up with the Electron internal code and leaking the IPC module, which is useful for us to talk to the main process directly. So let's see our case study 3, local file read in Microsoft Teams. So it was using the latest version of Electron, which is Electron less than 15. The remote module is completely removed, so we can't use remote module to get remote code execution. And we need to find an XSS, right? We found an XSS in one of the renderer where if you send a message to the victim, you can pop the XSS there. So we found an ODE in CK editor. This is the CV for that. So the XSS where we are in has node integration disabled, sandbox is enabled, but the context isolation is disabled, which means you can use the prototype pollution gadget to leak the IPC using the XSS and send an IPC to the browser process, which can read the file path, which can read the file in the local victim's computer. So there is this Electron internal IPC misconfiguration where the main process is listening for Electron native image create thumbnail from path. So if you send this IPC message to the renderer process with a path to the file you want to read, it will read that file and send it back to you. How fun it is. Like, it's a sandbox bypass, right? So this is the demo for that bug. When we paste the message to the victim, like when you send a message to the victim chart, it will open a new window and leak the JWT token of victim's Microsoft Teams, and you can do account takeover. So this is fun, and Microsoft paid $3,000 bounty for this. And let's increase the restrictiveness more. Let's increase the restrictiveness to the most, which means we disable the node integration, enable the context isolation, and sandbox the window, which means this is the most restrictive web preferences in Electron, and it is very hard to get remote code execution here because it's sandbox, context isolation is enabled, and node integration is disabled. So this is where we are in the architecture. So as you can see, the process is sandbox, there is an isolated context and stuff. So is it like a XSS in a browser? So in XSS, if you have XSS in a browser, you can just steal cookies or do some CSRF and stuff, right? but in Electron, the scene is different. Electron is a bit different from the Chrome, as it is a combination of framework layer code and browser code, right? So you can mess up with the Electron added code and get to do some stuff. And we'll see them in the coming slide. And this is where our actual talk starts. So let's see our first case study. We reported to the Electron Foundation, and they fixed the bug and gave us this CVE, which is enabling node integration in subframes from compromised render. So let's first understand what is node integration in subframes. Usually in Electron applications, the iframes don't have access to node shared library or preload scripts, which means you can't have access to node shared library in iframes. So they introduced this experimental option where enabling this node integration in subframes web preferences, you can enable Node.js or preload scripts in subframes, such as iframes and child windows. So for every subframe, if node integration is enabled and sandbox is disabled, then both preloads and Node.js will be available. If node integration is disabled and sandbox is disabled or enabled, then all preloads will be loaded, but node integration will not be available there. So let's see a basic example as we saw in the first slide. So in the right block, we have a main process where it's using an web preferences node integration in subframes to false, and it started an IPC event listener. As I said, using the preload script, you can expose that IPC open URL to the main page, and in the google.com page, it can be able to access window.electron.open URL, which is exposed by the preload script, but it also loaded an iframe, which is pawn.af, but this iframe can't access to window.electron.open URL because node integration in subframes is set to false. What you can do is, if you set this web preferences to true, you can expose the window.electron.open URL to the iframe, and iframe can access to preload scripts. So why we need this? Why we are talking about this node integration subframes web preference now? Most of the time, we get an access in an iframe. As you can see in the first Discord RC exploit, we got an access in video embed, which runs in iframe. Even in Microsoft Teams, we got an access in an iframe, and also VS Code, which is an iframe too. So most of the time we get an access in iframe, and we don't have access to much of the stuff like preload scripts, Electron internal APIs and stuff. So how Electron implemented this setting is, they patched the Chrome Blink web preferences, and they added these settings. As you can see, they added node integration subframes. By default, it's set to false to the web preferences, Blink web preferences object. So they also added node integration in workers, web view tag, and preload scripts, and all stuff. They added this there. And the check is done on /lel/renderer/electron sandbox renderer client.cc, and they are fetching the web preferences and checking if the node integration is enabled or not. If you carefully check, the check is taking place in the renderer process, which means using a V8 exploit, you find the offsets to this web blink preferences, and there you override the web preferences and get access to node modules. Let's see how we can do that. So if you notice that the process is running in the check is running in a renderer process, right? So we just use in renderer exploit to set the node integration to 1. So this is the exploit we used. So after the JIT exploit we have, we get arbitrary read and arbitrary write. And using that arbitrary read, we find the offsets to web preference. And then there we find the offset to node integration in subframes, and we override that node integration. We are just flipping the bit to 1. So we set to 1 and override that, and bam, like we got access to node integration. So let's see the case study of this bug. How many of you use Element here? It's also like Slack, but it's more secure, they say. So it's using Chrome version 91, which means quite old there. And as if the Chrome version is 2 versions old, you can get a JIT exploit if you are good enough to read the commits and reverse the exploit. So we found an XSS on one of the embed using deep link misconfiguration, but the context bridge is not enabled because we are in the iframe, we can't get access to preload scripts, right? So we run the V8 exploit to expose context bridge API on the embed and access sensitive stuff. This is how the element application is. On the right block, we have the main process, which started an event listener on the main process, and it is sending the path of that path to shell.open path, which is a dangerous sync. If you send a location of the binary, it will execute that. So they started an event listener, but our iframe won't have access to it. So this is the main JS. We have an RCE sync, and the preload JS is exposing that a preload JS has access to IPC, right? So it can send a message to main process, but and also it exposed context bridge to the main window. So the iframe we are in, the iframe where we have accesses, we can't access that window.electron.send because node integration in subframes is set to false. So what you do? You run a V8 exploit, create an iframe. It sets the node integration in subframes to 1 and creates an iframe, and there we can access the window.electron.send. This is the exploit we used. So as you can see, we are finding the offsets to node integration in subframes. We are flipping the bit and then creating an iframe and accessing electron.send user download mpen with a calculator path. So it pops the calculator. So let's see the demo of it. So whenever a victim clicks on link, it opens a element window. And if he joins the conference, it runs a V8 exploit and changes the offsets and flips the bit and can pop the calculator. It's still running the exploit. So it runs the exploit and pops the calculator. So this is the final part of our talk. Let's increase the restricting. Let's see one more case study. Now, can we disable context isolation? Let's see. So similarly, same case. They patch the blink web preferences and add this context isolation, and by default they set to false. What you can do? The check is taking place on the render process. So they're checking if they should create an isolate context or not. So if you can flip this bit, you can just enable the context isolation. So same story. Use the V8 exploit and set the context isolation to false. You find the offsets, flip it, and pop the calculator. So this is an RC in an undisclosed app. They didn't allow us to disclose, and they paid an hefty bounty to not disclose this bug to public. So in the main process on the right block, we have a open external IPC event listener, which is sending URL to dangerous sync of Electron. So this is the exploit scenario. We have the main JS where we have an RCE sync, and preload JS can access this, and also the main window website, but our XSS can't access this, which means use node integration in subframes exploit 0 to 1, and no, we can't access because now we don't even sorry, I forgot to tell something. Here, in the preload scripts, they are checking if the URL should be HTTP or not. So if you send an URL with file protocol, it won't allow us to open it. So we can't use the previous node integration in subframes exploit. So what you use a stage 1 V8 exploit to enable disable context isolation, and we redirect to prototype pollution gadget window, and there it can leak the IPC and directly access the main process. So we are not going through main window website, preload script, and Node.js. We are directly sending the IPC to the main process because we are able to leak the IPC directly. So this is the exploit, similar story, and let's see the demo. So it's trying to find the offsets of that web preferences, and after finding the offsets, it will override the context isolation object, and we can pop the calculator. So these are the offsets. You can find full exploits on my blog. this is about exploitation. Let's see the mitigations about these bugs. So there is a noticeable patch gap between Electron applications and Chrome because if there is a JIT bug in V8, they update immediately. But Electron takes some time to update the Electron version. And also the actual the Electron application like Discord, they are so backlogged, they won't update this JIT exploit, which means all of the Electron applications you use are vulnerable to JIT exploits in V8. So you always have a renderer exploit. It's always good to update your Electron application time to time and uh, enable all the security flags and mitigate all the web application security vulnerabilities such as XSS, open URL direction, even on all the subdomains. Don't implement sensitive IPCs. So we used sensitive implemented IPCs to pop the calculator right. So don't use that. And that's it. So in epilogue, we were able to achieve remote code execution in 20 different Electron applications like Jupyter Lab, Mattermost, Rocket Chart, Notion, Basecamp, and many more. So this is the research team, me, Aditya, William, and Max. And thanks to the other collaborators, Uday, who helped me in V8 exploits, Sergi, who helped in XSS, Tersang, Masato, and Harsh Jaiswal. So, any questions? So, if you want to test your Electron applications, you can mail this. You can find it. You can send a mail here. Any questions?
Does anyone have any questions? Last call. Okay, thanks a lot, Mohan.